Okay, great, thank you. So I want to start by thanking the organizers for giving me the opportunity to speak today. I'm actually going to talk mostly about what I did in my PhD at the University of Cambridge and sort of wrapped up here during my postdoc. So as you can probably guess from the title, I'm going to split this talk up into two parts. The first of which is going to focus on galaxy clusters and how they influence quiescent galaxy size growth. So to start with, I'm going to start with this well-known observation from the literature, which shows that there's a rapid size evolution at fixed stellar mass for quiescent galaxies with redshift. And two physical explanations emerged in the literature that could explain this rapid size growth. The first is a minor mergers hypothesis of size growth, which came about from observations showing that the number density of compact quiescent galaxies dramatically declines after a redshift of 2. And it was thought their disappearance can be explained if these compact galaxies have undergone gas-poor mergers with galaxies of very different stellar masses. And this has an effect of inflating the size by the stellar mass squared. The other option is that there is an addition of recently quenched galaxies to the quiescent population. And this came about from some observations showing that the number density of compact quiescent galaxies actually doesn't change with redshift, shown in this black circle here. But what does change is the number density of extended quiescent galaxies, shown with arrows. So on the right-hand side of the fence, it was thought that the rapid size evolution is actually due to star-forming galaxies, which are larger at fixed stellar mass than quiescent galaxies, quenching and joining the quiescent population at the large size end. So for a while, there was intense debate in the literature about which of these physical mechanisms was dominating this size growth. And one way you can actually test the minor mergers hypothesis of size growth is by using environment as a laboratory. So satellite galaxies in clusters are actually moving at very high speeds, making mergers between them rare. But the opposite is true in the field environment. So if the minor mergers hypothesis is true, cluster quiescent galaxies should actually be smaller than field quiescent galaxies at fixed stellar mass. So to do this experiment, you need a statistically significant sample size of cluster galaxies to be able to measure a size offset reliably. And I use data from the GCLASS survey, and that's a spectroscopic survey of 10 rich infrared clusters at about a redshift of 1. They have about 500 cluster members, and we obtained 38 orbits worth of HST wide field camera 3 Grism follow-up in cycle 22. So the HST data is actually what allowed this study to be possible, as well as providing high spatial resolution imaging for reliable size measurements. The Grism spectroscopy actually helped to increase our sample of cluster galaxies. So using galaxies that had spectroscopic, photometric, and Grism redshifts in the survey, we were able to identify a selection threshold in Grism redshifts that allowed us to identify cluster members with 90% purity. And this can be seen by the tight clustering of green points here in the right-hand panel. These are Grism redshift selected cluster members with a spectroscopic redshift to support the reliability of their cluster membership. So the high precision in Grism redshifts relative to photometric redshifts allowed us to boost our sample size of cluster members by more than 50% of the existing spectroscopic sample. So after we've got our giant sample of cluster galaxies, we can do the mass size relation measurement. And this is what the mass size relations look like at redshift 1 in both environments. And what we're going to do is we're going to calculate the size difference between quiescent cluster and field galaxies. On the left-hand side here, you can see what our result is, which is on average, we find that quiescent cluster galaxies are 20% smaller than field counterparts at fixed stellar mass. And on the right-hand side of this slide, if we track this size offset back in time, we see that it's actually consistent with the quiescent field relation at about a redshift of 1.2, suggesting that the lack of minor mergers has inhibited the size growth of quiescent cluster galaxies. But at low redshift, results show that the quiescent mass size relations are about the same in both environments, meaning that despite this minor merge suppression, the cluster environment has to catch up with the field by redshift 0. And we actually showed in my first paper that this can actually be achieved if you consider cluster-specific processes where the compact galaxy population is destroyed by merging with either the BCG or being tidally destroyed into the ICL. And this is completely consistent with the observed stellar mass growth of BCGs between a redshift of 0 and 1. and the observed ICL stellar mass fraction at about a redshift of 0. However, we have to consider that between a redshift of 0 and 1, larger quiescent galaxies in the field that have been growing via minor mergers will fall into the clusters, increasing the average size of cluster quiescent galaxies with redshift. So this idea of larger quiescent galaxies being added to the large size end of the quiescent distribution nicely brings me to the second proposed mechanism suggested for the rapid size evolution of quiescent galaxies, and that is the addition of recently quenched galaxies to the quiescent population. So since we have a population of spectroscopically identified recently and rapidly quenched galaxies in the clusters, we can actually see where they lie on the mass-size relation, and we find direct evidence in the clusters that recently quenched galaxies are on average larger than quiescent galaxies, as shown here, showing that the second suggested mechanism of size growth also contributes, as well as minor mergers. So talking about recently quenched galaxies and clusters naturally brings me to the topic of galaxy clusters and quenching. And to start off with, I'll give a quick overview of the current consensus in the literature, which is that Wetzel et al. In 2013 proposed the delayed then rapid quenching model to explain the indistinguishable star formation rates and high quench fractions in redshift 0 clusters compared to the field. In this model, galaxies continue forming stars as they are accreted onto the dark matter halo of another galaxy, but their star formation rate isn't actually affected straight away. Hence, there is a delay before environmental quenching begins. Then a rapid catastrophic event quenches the galaxy, making it difficult to measure any gradual change in the average star formation rate. High redshift studies have found that the delay and quenching times become shorter, with work on the G-class clusters in particular finding they are about 2 times shorter at redshift 1. So these results therefore advocate for rapid environmental quenching at high redshift. Most studies try to constrain environmental quenching using indirect methods with population studies such as measuring quench fractions, timescales, and star formation rates. But the purpose of my PhD was to use a direct method at high redshift for the first time, and that is space-based slitless or Grism spectroscopy. Space-based slitless spectroscopy allows you to obtain low-resolution 2D spectra of all the sources in your field of view. Each streak you see here is actually an image of the galaxy at every single wavelength with some overlap. And by processing Grism spectra, you can actually obtain emission line maps of galaxies. At redshift 1, we can obtain the H-alpha emission line map with the long wavelength Grism on the HST wide field camera 3. And H-alpha emission traces emission from young, hot OB stars with lifetimes of about 10 million years. And so we can trace star formation on very short timescales. The HST direct image of our cluster provides us with a 2D map of the stellar continuum, or the integrated star formation history of a galaxy. You can then stack these maps in bins of stellar mass, shown here, measure the mass-size relation in 2 different traces, allowing you to get a handle on where star formation in the galaxies is happening more recently versus where it was happening in the distant past. This experiment was done in the redshift 1 field environment here, where they found that H-alpha is actually larger than the stellar continuum at every single stellar mass, suggesting that galaxies are growing in an inside-out fashion via star formation. So we applied the same technique to the clusters in the hope it will give us some insight in how environmental quenching is operating at these redshifts. And these are our results using this technique. So on the left is the field relation, next to it is the cluster mass size relation that we measure, and then here is the difference between the field and cluster environments. And what we find is that the H-alpha over continuum size ratio is actually smaller for cluster star forming galaxies by 6%, but given the error bar is statistically consistent with environment. So this is surprising because we know from previous work on the G-class clusters that environmental quenching is happening in these clusters due to the high quench fractions measured. However, we also know from previous work that the G-class clusters have an indistinguishable star-forming stellar mass function from the coeval field. So if you put these 2 results together with the now indistinguishable H-alpha to continuum size ratio with environment, we can infer that there is rapid environmental quenching going on in clusters at redshift 1. In other words, the star-forming cluster galaxies have yet to undergo environmental quenching since they are still in the delay phase of environmental quenching. So since the star-forming cluster galaxies are likely in this delay phase, we then examine the recently quenched cluster galaxies I spoke about earlier using the same method and compare their properties to the star-forming cluster galaxies to see if it can tell us anything about how environmental quenching actually operates. Surprisingly, 87% of them have H-alpha detections, suggesting residual star formation, with star formation rates a factor of about 8 lower than the cluster star-forming galaxies. The H-alpha continuum to size ratio is 81% smaller than the field star-forming galaxies. So not only are the H-alpha disks fainter, they're also smaller than their star-forming counterparts, suggesting rapid environmental quenching in redshift 1 clusters happens outside in. So what's interesting is that these results are consistent with the delayed then rapid quenching model. This plot shows a compilation of results in the literature that use the same technique as us of measuring the spatial extent of the star-forming disk versus the stellar continuum in clusters and field star-forming galaxies over a wide range in redshift. In the delayed then quenching rapid model, our redshift 1 result for star-forming and recently quenched cluster galaxies represent the two extremes in the range of disk truncation values we can expect to measure from outside-in environmental quenching. And so if outside-in environmental quenching operates over longer timescales at lower redshift, we should expect to see disk truncation measurements lying midway between those seen at redshift 1. And that's actually kind of what we see here. So our results therefore have the sensitivity to confirm that the environmental quenching process evolves with redshift when comparing to the literature. So just to conclude, the first conclusion I have is Grism-derived redshifts have 4 times higher precision than 12-band photometric redshifts. So people who work in cluster astrophysics, this is a very cheap way of getting redshifts for everything in your field of view, so please consider it. At redshift 1, we find quiescent cluster galaxies are smaller than their field counterparts at fixed stellar mass. So this is evidence that minor mergers drive the rapid size growth we see in the field environment. The low redshift field and cluster quiescent mass size relations can be reconciled if you consider cluster-specific processes. I also showed you direct evidence that recently quenched galaxies contribute to this size growth, so everyone can stop arguing, basically. And finally, I've shown you this somewhat exciting result, I think, that there is direct evidence of rapid outside-in environmental quenching in cluster galaxies at redshift 1, which is consistent with the delayed then rapid quenching model. And we find that the environmental quenching process evolves with redshift. Thank you.